sketching graphs. We're going to put together everything we've done so far. So we're going to draw an accurate graph. This time accurate, we care about the high points and the low points. If y equals x squared minus 1 over x squared. We find x-intercept, y-intercept, from both asymptotes. To find an x-intercept, you let y equal 0. We'll bring the minus 1 over x squared over and multiply both sides by x squared to eliminate that denominator. When we do that, we get 1 equals x to the 4th. And what can I raise to the 4th power and get 1? Plus or minus 1. So we have 2 x-intercepts. Y-intercept, you let x equal 0. We are never allowed to divide by 0, so there's no y-intercept. Vertical asymptote. We're looking at the denominator. What are we not allowed to have in the denominator? And what would make that 0? 0 would. And that makes perfect sense. If there's no y-intercept, we expect a vertical asymptote of 0. Horizontal or other. Take the limit as x approaches infinity. When we do that, infinity squared minus 1 over infinity, this part will give us 0. And this part gives us infinity. And when we get an answer of infinity, we say, what gave us the infinity? The x squared did. So we have an asymptote of y equals x squared. Then the critical points. That was y prime equals 0. So we're going to take the derivative. You'll be better off if you write it as x squared minus x to the negative 2. So the derivative, we would get 2x minus 2 times the minus 1 is plus 2 x to the minus 3. And then we'll rewrite that with a positive exponent. So our derivative is 2x plus 2 over x cubed. We said critical point, let y equal 0. We'll bring the 2 over x cubed over, multiply both sides by x cubed to clean out that denominator. That will give us minus 2 equals 2x to the 4. And at this point, you can stop. We're raising something to the 4th power, multiplying by 2. Is it possible to end up with a negative? The answer is no. If you don't see that, feel free to divide by 2 and get negative 1 equals x to the 4th. And then ask yourself, can you raise x to an exponent of 4 and get a negative? Nope. So there's no solution. That means there are no critical points. We still draw the number line. We put on our vertical asymptote of 0. And we're plugging it into the derivative. Okay, let's find some numbers. Nice easy number on the right would be 1. 2 plus 2 over 1, that's definitely positive. Easy number on the left. I've got negative and more negative, so that's negative. And here's our plus minus chart. So where it's positive, we're increasing. So from 0 to infinity, we're positive. And where it's negative, we're decreasing. So from minus infinity to 0. We need to find the y value for the critical point, but that's an asymptote, so it doesn't exist. And so if there are no critical points, we are done with that. Okay. Now we're going to do the same thing again. So let's just back up again. We took the function, found the derivative, let it equal to 0. Drew ourselves a number line, picked out the plus and minus points. We're going to do it one more time. We don't know why yet, but just bear with me. So the derivative is 2x plus 2x to the negative 3. We are going to take the derivative of the derivative. So it's known as the second derivative. Derivative of 2x is 2. Derivative of 2x to the negative 3 is negative 6x to the negative 4. We're going to let that equal 0, just like we did before. Bring that over and we'll solve it. Multiply both sides by x to the 4. So we'll get 6 equals 2x to the 4. Let's divide both sides by 2. What can you raise to a 4th power and get 3? Well, you could put 1 over 4 on here. And when you do that, you have to remember that it could be plus or minus this answer. So plus or minus the 4th root of 3. So now we're going to draw ourselves a number line. On the number line, we're putting the 4th root of 3. the negative 4th root of 3, because those are our important points. We don't know what they suggest, but we'll get there. We also put our vertical asymptote. Okay, nice easy number in between. Now, is 1 in between? You can check it. The 4th root of 1 is 1, so the 4th root of 3 is bigger. So we're 100% sure that 1 is between these two numbers. We're plugging into the derivative. We plug 1 in, 2 minus 6, I'm getting a negative. Bigger than the 4th root of 3. How about 100? Pretty confident that's bigger. 2 minus 6 divided by 100 to the 4th. That minus 6 to the 100 to the 4th is going to get wiped out. Now on the other side, whether I put in a plus or minus number doesn't really change anything, meaning when I'm plugging in negative 1, I get the same answer as when I put in 1. Because 2 minus 6 over minus 1 to the 4th is the same answer as 2 minus 6 over 1 to the 4th. So I can very quickly see that these two answers are the same and those are the same. So there's our plus minus chart. And what does this actually tell us? Well, I'm so glad you asked. So when the derivative changes, it tells you how the original function is increasing or decreasing. So when the second derivative changes, it tells you how the slope is increasing or decreasing. So anywhere this is positive, it means that the slope is increasing. Let me just back up and try that again. When the derivative was positive, this one was increasing. So when this is positive, this one is increasing. So slope increasing. Super negative slope, kind of negative slope, zero slope. Kind of positive slope, super positive slope. So when you have a positive on the second derivative, it tells you that your graph is concave up because your slope was very negative, not so negative, zero, kind of positive, super positive. So when the second derivative is positive, your slope is increasing, which gives you a concave up shape. So from minus infinity to minus 3, and the 4th root of 3 to infinity, we're concave up. What if it's negative? If the derivative is negative, let me just get rid of those and show you. If the derivative is negative, the original is decreasing. If the second derivative is negative, the first derivative is decreasing. So what does a decreasing slope look like? Super positive, not so positive, zero. Kind of negative, very negative. That's a decreasing slope. Talking about concavity there, that's concave down. So anywhere the second derivative is negative, the original graph is concave down. And concave up is when your curvature is up, concave down, your curvature is down. This is how I remember that positive is up and negative is down. You can think of your concavity, radio antennas look like this. You have this little thing that collects all the waves. If that is pointing up at all, that's concave up. If it is pointing down, that's concave down. So that's the difference between concave up and concave down. These are known as your points of inflection. So when the derivative was equal to 0, it gave us critical points, maxes and mins. And when the second derivative equals 0, it gives us something called a point of inflection. A point of inflection is when your concavity is changing from either up to down, so that would be a point of inflection, or from down to up. It tells exactly where that curve changes. And where did these numbers come from? We took these two x values, plugged them into the original, and then calculated what y was. So you try that, plug them into the original, and see if you get the same answer. Now, let's graph. So this is all the information we found, and let's start with all the points. X-intercept, -1, +1. No y-intercept, vertical asymptote at 0. Horizontal asymptote of y equals x squared. So y equals x squared, Goes through 1, 1, 2, 4, 0, 0. So this is going to be an asymptote, a line that the graph approaches. I should draw that dotted. And then let's see what other points we have. There we go. Okay, what else do we have? We have a point of inflection at the fourth root of 3. So you're going to calculate what the fourth root of 3 is. I'm just going to grab the calculator and see what it says. So 3 to the exponent 1 divided by 4. I'm getting an answer that is wrong. So let me try that again. 3 to the exponent 1 divided by 1.316 it says. Let's see if that makes any sense. 1.316. So at 1.316, 1, 2, 3, we're at 1.15. Somewhere around here. Same thing is true on the other side, negative 1.3, 1.15, somewhere around there. All right. Then I recommend you use your concave up and your concave down to draw the rest of the graph. So from minus infinity to minus the fourth root of 3, we need to be concave up. So I can't come down. I have to approach the asymptote. I'm going to get another color and see what's going on. So from this point, approaching asymptote concave up. That looks like it might make sense. Concave up on the other side as well. Let's try that. Concave up. The rest of the graph is concave down. So between these, my curvature changes. So I'm now going down past that point and approach that asymptote. Do the same on the other side. Concave down, the curvature is down, curling towards that asymptote. Now I check my work with my increasing and decreasing. I might have decreasing appearing in a minute. So increasing from 0 to infinity. Oh, yes, it is. As we go left to right, that's going up. Let's see if I put decreasing on. I didn't. Okay, silly me. It's decreasing for the rest. So decreasing. So it looks like our graph is good. A little shaky. That's better, but that's really what we had drawn. And so what we did again, we put all our points on. So any points of inflection, any x-intercepts, any asymptotes. If there had been critical points, we would have put those in again. Then we connected the dots using concavity. The graph curves upwards. It's a little hard to tell. You can see that this is an upward curve, so this one should match it. That's curving up. This one is curving up. And this section, you can sort of see that if you were put in a little radio antenna, that it'll be pointing down. So that's a downward curve. All right, these take a lot of time. I'm only giving you 3, and then we're just going to keep working on this for a bunch of days. So just do a whole pile of graphs. The more you do, the better it gets.